To start with our first example of IEEE 754 floating point representation, let's assume that we have a number which is this 91.6868875. This is 6. So 91.6875. What would be the IEEE 754 representation of this value? To come up with that IEEE representation, we need to convert this 91 into binary form as well as this 6.6875 into binary form. So if we represent 91 into binary, then the value would be 1 0 1 1 1 1 1 0 1 1 0 1 1 0 1 1. This would be the binary representation of 91. Similarly, 0.6875 can be represented as 0.1011. 1011. This is the representation of this fraction value. So what is the total representation of 91.6875? This is 1011.1011. So this is the representation of 91.6875. Now next part is, according to the conversion process, the next part is to uh, represent it into normalized form. So let's say the normalized form would be 0 1 1 0 1 1 1 0 1 1 into, since this is binary value, 2 to the power how many bits? 1 2 3 4 5 6. So this would be 6. So this is a normalized representation. Now the next step is to represent this exponent into bias notation. Let's call that bias notation as Q. So what we'll do, we'll have 127 plus 6, which is 133. 133 in decimal. Equivalent binary of this one is 1 1 0 0 0 0 and then 101 101. This is the binary representation. So how many bits do we have here? 1 2 3 4 5 6 7 8. So this is our exponent for the format. Now we have all the representation. What is the sign of the value? This is positive value. So the sign would be positive. That means we'll have a 0 here. We'll have a 0 in the sign bit. So this is our sign bit. So we'll have a 0. And then we have exponent bit. So what is our exponent? 1 0 0 0 0 1 0 1. So we'll write 1 0 0 0 0 1 0 1 and the rest. So this is our exponent bit, this is our exponent field. We have this is 1 bit and we'll have 8 bits here, and then the rest is our fraction bit where we'll have 23 bits. So it's 0. I'm taking the fraction from these bits: 0 1 1 0 1 1 1 0 1 1. Since we do not have anything, so the rest will be 0. Now there will be 23 bits, which is our fraction. Now this entire representation is our IEEE 754 floating point representation of the value 91.6875. So this is how we represent this value 91.6875 according to our IEEE 754 floating point formatting. Now we shall see how we can convert a hex value into equivalent decimal value using IEEE 754 floating point representation. So first write the, let's have the hex value. So this is 3, C, 8, and the rest of the values will be 0. So this is our hex value. To convert this hex value into equivalent decimal value, the first thing that we need to do, we need to convert it into binary value. So let's convert it. So 3 is 0, 0, 1, 1. C is 12. So this is 1, 1, 0, 0. Again 12, 1, 1, 0, 0. And 8 is 1, 0, 0, 0. Since rest of the bits are 0, so we can write it in short like this. Now, as we can see from the binary sequence that the MSB bit is 0, which means whatever the decimal value that we might come up with will be a positive value. Now, next we will consider next 8 bits, which will be this 1, 2, 3, 4, 5, 6, 7, 8. So, this 8 bits, this is part of the fraction. Let's call it Q. So, Q is 0, 1, 1, 1, 1, 0, 0, 1, which if we convert it into decimal, this would give us 121 in decimal. Now remember that when we are converting decimal value into binary equivalent using IEEE 754 formatting, we added 127 just to make the exponent positive. So we know that in this 121 we have 127 in it, so we need to take that 127 out of 121. So the actual exponent is E, and the actual exponent E can be found just by subtracting 127 from 128, which would give us -6. So the binary representation would then be the 1 coming from the normalized form, and then we have this value, which is 1, 0, 0, 1, and then into 2 to the power -6. Now we adjust the decimal point, so this will be 1, 2, 3, 4, 5, 6, 1, 0, 0, 1. So this is the uh, binary representation of our decimal value. Now this is -1 position, -2, -3, -4, -5, -6, -7, -8, -9, and this one is -10. So if we try to convert it into decimal value, then we'll have 2 to the power -6 plus 2 to the power -7 plus 2 to the power -10. If we do the calculation and do some kind of some form of simplification, then the final value that we would get would be something like 0.0244140 and so on. So in short, we can say that this hex value is equivalent to, let's say, 2.0.0244 decimal value. Okay, so this is the this hex value represents this decimal value. So using IEEE 754 floating point representation, from hex value we can also represent actual decimal value. Now we shall see how we can convert a negative value into binary value using IEEE 754 floating point representation. Let's assume the negative value is 0 -0.637. The first thing that we need to do is we need to convert this 6.637 into binary value. how can we do that? Let's see some step. 637 multiply, we need to multiply it by 2, and which would give us 1.2, 1.274. So we'll take this 0.274 multiplied by 2, which would give us 0.548. We take this, so 0.548 into 2, which would give us 1.096, and so on. So it continue this multiplication process to get the binary representation of 0.637. This bit is the MSB bit, and as we go down we get the LSB bits. So the binary equivalent of the of 0.637 is, or rather minus 0.637 is, minus 0.101101 triple zero triple zero 11 triple zero 100 100 100 triple 100 So this is the binary representation of our decimal value. Now if we represent it in a normalized form, then this is how it is going to look like: 0 0 0 1 1 0 0 1 0 0 1 1 1 into 2 to the power minus 1. So this minus 1 is our actual exponent. So exponent E is equal to minus 1. Now if we'd like to represent this exponent into the bias notation, let's say this is Q, so we need to add 127 with it, 127, which would give us 126 in decimal, and the representation of this one in binary is 0 6 1 1 2 3 4 5 6 and 0 in binary. So this 8 bits represents the biased exponent. So in the IEEE format, what would be the representation then? Our value is negative, so we'll have an 1 in the sign bit, and exponent is this one, so this is 0 1 1 1 1 1 1 0, and the fraction bit are going to be this, so which is 0 1 0 0 0 1 1 0 0 0 1 0 0 1 0 0 1 1 1. Now this is this binary value. This binary value is the IEEE 754 representation of our decimal value, this. Now from this there is another one step that we can do. We can represent this value in hex. To do that, we can represent this part. We can take 4 bits from here. We can take 4 bits from here, 4 bits from here. We can take 4 bits, and then we can represent them in hex. Now this is 8 8 10 11, which means this is B, and this one is F, this one is 2, this one is 3, this one is 1, this one is 2, and this one is 7. So this hex representation is the representation of this binary decimal value if we convert this decimal value into IEEE 754 representation. This time we will be converting a hex value into equivalent decimal value, which already have seen in previous slide, but this time the value is little bigger than what we already have seen. So the hex value is F F 7B and the rest is 0. Rest is 0. We need to convert this hex value into equivalent decimal value using IEEE 754 floating point representation. To do that, the first step is we need to convert the hex value into binary value. So F is 1111, the second F is 1111, 7 is 0111, and B is 1011, the rest is 0. From the sequence of binary bits, we can identify that the actual value will be negative. Then we need to identify the next 8 bits for the exponent. So this is 1 2 3 4 5 6 7 8. Now if it's q, so q is 1 1 1 1 1 1 2 3 4 5 6 7 8, which is 254 in decimal. We all know that we have 127 inside this one, 254, so the actual exponent would be 254 minus 127, which is 127. So the representation normalized form would be 1 point, this part, which is 1 1 1 1 0 1 1 into 2 to the power 127. What we can do, we can write it like this: 1 1 1 1 0 1 1 into 2 to the power 120. How many bits did we take? 1 2 3 4 5 6 7. So that 7 bit will be subtracted from this exponent. So we have this value into 2 to the power 120. Now what would be the equivalent decimal value of this one? Equivalent decimal value of this one would be 2 to the power 127 plus 2 to the power 126 plus 2 to the power 125 plus 2 to the power 124 124 plus 2 to the power 123 plus 2 to the power 121, and then 2 to the power 2 to the power 120. So 2 to the power, let me write it, 2 to the power 120. Now the equivalent decimal value would be 3.3 into 10 to the power 38. If you put it into the calculator, then you would find, if you put this value into the calculator, then you would find this final result. Now how did I find these values, these powers? See, we have 120 as the exponent here. So if we come this side, then this would be bit 127, because this is in the positive direction. So this the in the positive end, its bit position starts from 0. So this is 0, this will be 0 1 2 3 4 5 6 7. Since we already have exponent 120, so this first position would be 120. So this one 21, 22, 23, 24, 25, 26, and 127. This is how it works. So this is the decimal representation of the hex value that we have. here. Now we shall be looking at something which is a bit different than what we have been doing in this lecture. We shall be looking at a situation where the value that we are dealing with has to be stored in a register that is not 32-bit. Let's say the register size is arbitrary. In our case, let's assume the register is of 18 bits. So now we have 18 bit register, which means the cells that or the bits that will be assigned to various field are going to be different. Yes, sign will have 1 bit, and then exponent will have 5 bits in this case, and the fraction will have 12 bits. So this is our 18 bits. Now let's see how we can convert a decimal value in IEEE 754 floating point representation, but in this case the register size is 18 bits, the one that we just discussed. So let's say we have a value which is 13.75. We all know what we need to do next. We need to come up with the binary representation of this one. So the binary of this one is 1101, 1101.11. This is the binary representation of 13.75. Next, we will be representing it in a normalized form, which is 1.10111 into 2 to the power 3. Now we need to come up with the we know the exponent is 3 from this value, but we need to come up with the biased expression, biased exponent, which we have been indicating with by Q, using Q. So what would be the value of the biased exponent? Because when we were using 32-bit registers, we used to add 127 in case of when we are generating biased exponent. But in that case, exponent had 8 bits. Here, exponent has 5 bits. So how what should we add with the actual exponent? Now a general formula that you can use is something like this. It's 2 to the power number of bits in the exponent minus 1, and then you do in minus 1, because we start from 0 in both cases. That's why we have minus 1 here and we have minus 1 here. So uh, now let's see how this formula works. Let's assume that our register size is again 32 bit. So we'll have for 2 to the power 8 minus 1 and then minus 1. This would give us 127. But for according to this configuration, so what we'll have? We'll have 2 to the power 5 minus 1 and then minus 1, which would give us 15. That means to get the biased exponent, we need to add 15 with it. So we'll be adding 15 plus 3, which would give us 18, and the binary equivalent or binary value for 18 is 1 0 0 1 0. So this is our biased exponent. So the representation would be according to the our new format, which is 18-bit register. Our value is positive, so this will be 0, sign bit will be 0, and then the exponent, which is Q here, 1 0 0 1 0, and then our fraction bit, which is this, which is 1 0, 1, 1, 1. And this is our representation IEEE 754 floating point representation with a register which is 18 bit in length.